Okay, we can start the last session of today. It's going to be very informal, as I mentioned in the email. So we're going to discuss some open problems. And so if you if you fill the form, I will have your keywords for the question you suggested. And I'm just going to go to some random list, not totally random, but we're going to start with Melissa, because she spoke just before. She's warm. And she's going to basically, every person is going to take 5 minutes at maximum to tell about open question. You can also take 30 seconds, as long as it's clear it's self-contained. And afterwards, well, it could be open questions to anyone. If you have any comments, you can basically have an open discussion, but we can also go further if there are no comments, if the question is too complicated. So yeah, Melissa is now prepared for the question.
So, this will not be as well formulated as it would have been if it was a call than we half an hour from now when I would work out some examples, but I will go anyway. Okay, so yeah, the setting for my open problem is still the Amplituhedron. And yeah, maybe I'll state it in general first. So the question is pretty easy to state. So let S be some sort of cell in your Kn of dimension say b greater than k times m. The question is, okay, so because the dimension is bigger than k times m, there is absolutely no hope for the image of this thing to be a tile. Right? It's going to be bigger. And the question is, can the image be tiled? So we have the image of this cell. And okay, so of course, if I choose my cell to be, yeah, okay, and I guess so if I chose my cell to be the entire totally non-negative Grassmannian, we know the answer to this question for, okay, yeah, so if S is equal to, sorry, the top cell, which is our Kn, we know the answer is yes, if M is 1, 2, or 4. Okay, so I suggest, I guess, asking this question really in one of these settings, m equals 1, 2, or 4. Otherwise, the easiest version of this question, we don't know the answer to. Yeah, so maybe the kind of like question prime is, let's just ask the question for like m equals 2. I guess you could probably also do m equals 1, but maybe m equals 1 is like basically implied by the results of Stephen Cohen and Warren Williams. I'm not totally sure, but maybe you could analyze it pretty well using their method. So I sort of, yeah, so my feeling is sort of that m equals 2 is maybe the first really interesting, like you have to come up with many new ideas to solve this setting. Right, I guess if you do restrict m equals 2, another sort of related question, which depending on its answer may or may not imply this one, is okay, so question double prime is in the m equals 2 setting of the question, is this image closure the union of some W chambers. Okay, so this is like not exactly the same as the question, because, okay, so, right, so sorry. W chambers, Rand discussed them in his talk. There's something that's sort of special for m equals 2 and that we don't know how to really make good sense of them for other m. But if you remember, W chambers are like, they're just a region of the Amplituhedron specified by picking the signs for every twistor coordinate. And all of the tiles are unions of W chambers. So if this thing had a tiling, it would certainly be a union of W chambers. You can also kind of like ask this separately, like, can you just write this as a union of W chambers? Okay, that's my question. Are there any questions about the question? 3 questions.
If you allow D to be equal to Km, do we agree that the answer is no? So you could pick S to be a degree 2 tile, degree 2 thing, then the answer would be no.
Yeah, I guess.
Or how would you allow that?
Okay, so yeah, so maybe I should. maybe I don't know.
Would you allow that or would you not allow that?
Think of a reason not to. I think it's still kind of an interesting question. So so maybe the bigger question is like, can images of positoroid cells be tiled? So maybe, yeah, what happens if it's degree 2, but does the dimension drop if it's degree?
No, degree 2, the dimension is the same. So I'm just wondering whether you would consider the answer yes or no to that particular case.
Well, I think we don't know, right? Because the tiles are always, the map is injective, it's degree 1 on the tiles.
Oh, okay. Then
Yeah.
I think,
I mean,
I thought it's no.
but it depends on what the image looks like. We don't have a characterization of all finite section numbers. That was the 5 minutes. Yes.
Okay.
No, but we can still continue discussing it. It's just the time.
Oh, okay, so I've stated the question. So
Yeah, that's the
yeah,
question.
okay, so are you saying you know the answer if I put equality?
Well, I have a particular cell in mind, like K equals 2, N equals 8.
Yeah, the four mass box.
Yeah. So do you consider the answer to that question yes or no in this case, or unknown?
Unknown.
Oh, you think the answer is unknown for that?
I mean,
particular-
we suspect no, but it's unknown. No, it's not proved. I think.
Oh, okay.
I mean,
Yeah, so
Okay.
I'm not, yeah, maybe I'll say one thing, right? So remember, tiling means it should be decomposable into disjoint tiles.
But do we know something about I think Mark wrote down some of the pose of the form. Could we rule out that it has a tiling just from that
Right,
alone?
so I think Mark was writing down something algebraically, which may not have a geometric counterpart.
Yeah.
So that has not been checked.
Yeah.
So yes, you're correct. If we could identify one of the things that Mark wrote down as honestly the thing like corresponding to a boundary of this image, then no
Yeah.
tiling. But yeah, that's part of the question.
I guess I wanted to add that for m equals 2, for full dimension, for s dimension greater or equal, I mean greater than 2m, greater than 2k, then our magic number will also imply if there is a tiling that the size of a tiling or every tiling is constant, right?
Yeah, right.
That's
Right, yeah, so something that Ron didn't say is that so he's talked about the magic number for tilings of the amplituhedron, but actually there's a similar statement where if you have a region of the amplituhedron which admits a tiling, then all tilings are the same size, and the proof is identical. Yeah.
But the missing part is understanding whether that's actually the tiling.
Right. So if you can answer this question like yes, then you also have a magic number phenomenon for this image.
Okay. Thank you, Elisa. Okay, so next speaker is Nima. No, sorry. Yes, Alex.
Question.
Yeah.
I don't know. Maybe related to analysis of actually.
Okay.
Yeah,
So,
you want
Question, but-
okay. So yeah, Nima, Alex has a question to pose. So yeah, you can come to the Blackboard.
I can ask it. Yes,
Okay.
I already kind of asked it during.
But do you want to come here such that everyone can see?
Okay. And again, I don't really know if it's how much open it is, but short question, can we define tiles and tilings without using matrix Z? Question is about definition of tiles and tilings. Is it possible to define them, just describe them combinatorially without using any matrix?
And easy.
Yeah.
For the amplituhedron.
Yeah, for the amplituhedron. So because, as Melissa said, it looks like this notion, her definition kind of a priori depends on Z. It looks like it's
Yeah.
independent, but is it possible to give another definition that doesn't use matrix Z? Well, maybe it may not be equivalent to this definition, but how can we define tilings and tiles just kind of abstractly. Like
Yeah, I
from the
mean,
graphs.
for m equals 2, there is a partial answer. I mean, in one way is that we found that for m equals 2, all the tilings are in bijection with some decomposition of the hypersimplex into positive polytopes. So, and only the tiles that are all Z tiles of the m equals 2 amplituhedron are in bijection with the finest decompositions of the hypersimplex into positary polytopes. Another side is that you can map the amplituhedron into a Grassmannian M, N, and in principle, that maps leads you to a subspace, so not full dimensional, that depends on Z, but you can upgrade that into full dimensional space if you think the amplituhedron has something defined only by some sign flip conditions on your Fluker coordinates of your Grassmannian. For m equals 2, we proved with Laura and Melissa the conjecture that m equals 2 amplituhedron can equivalently be described by sign flips. And if you take the same sign flip pattern and you use it to define a region, full dimensional region in the Grassmannian Chukoman, that you can ask a similar question about what are the tiles there. The tiles are regions in the Grassmannian Chukoman where a subset of Flukers have a definite sign. And then you can tile your amplituhedron into your Chukoman by these regions. So that is the kind of Z-independent version. In our paper, it appears as a G amplituhedron, but in physics, it was like momentum twister amplituhedron. So directly in the Grassmannian M, N, 2 or 4, according to or whatever you want. And those tilings are in bijection with the hypersimplex, the composition of hypersimplex, and don't depend on Z.
Okay, but for M, like for general
For general M is an open question, and
the question is how to describe them combinatorially. Like somebody gives you a Plebby graph, doesn't give a title. So
this for m equals 2 is fully understood. This one for general M, this is a great open question. For m equals 3 is still open question. Maybe I didn't formulate it here. It's open question even giving a collection of tiles. How do you tell combinatorially whether that's a tiling? We have some necessary condition, but still not sufficient. Okay, thank you. Yeah, so now Nima, can you hear us? Everything is good?
Yes, just say that I think Alex's question is wonderful, but in many ways is the kind of is running the history backwards. It was after many months of failing to find some combinatorial characterizations of the cells and purely in the Grassmannian that kind of gave the amplitude that we realized that they fit together in this space after we projected through Z. But that doesn't mean that there isn't a way of understanding it. It's just that whatever it is, for NMHV, for k equals 1, there's a very beautiful picture because you can really kind of map the sort of cells that map into the cyclic polytope. You can characterize very easily in the positive Grassmannian. There's a sort of boundary operator. You can define the standard boundary operator on the cells of the on the positoid cells. Does beautifully characterize the combinatorially the collection that tiles the cyclic polytope. But the analog of that for a higher K was what we failed mightily to find back then, which is what ultimately led to the picture projecting through Z. So, but it's a wonderful question. Maybe there is a way of thinking about it. That would be really fantastic. All right, so I have a general point I want to make. Oh, sorry, and then maybe one or two specific questions. The general point that I want to make is I think it's really fascinating that we can think about all of these adventures in combinatorics and positive geometry connecting to physics over the last 10 or 15 years as in one way or another being finding mathematical objects that reflect this sort of physics of factorization. That when you go to a boundary, the object simplifies in some way, splits, or simplifies in a way that exactly mirrors what the amplitude does. Now we found an embarrassment of riches. There's a number of ways that can happen with different ways of conceptualizing what the kinematic space is, either in the amplituhedron or in these new ideas involving surfaces. But one of the most surprising features of this whole story for me, especially as a physicist, is that typically you're used to thinking in physics when you run into some sort of mathematical structures that have something to do with quantum field theory or string theory, that eventually when you wander around, you'll discover that their origin in quantum field theory and string theory is king. It sits on top of the set of ideas, and then all the rest of them are sort of derivatives of it in some way. And that's emphatically not the case in this entire business. And it's a very mysterious and strange thing to me that the parts of these mathematical structures that connect to the physical world, as far as we know so far, are in some funny, no particularly privileged position in the set of all the objects involved. For example, in the Amplituhedron is m equals 4. That's relevant at tree level. But there's nothing especially special about m equals 4. There's m equals 2. There's higher m. In fact, the higher m objects are even more interesting in many ways. They're more mysterious, but they're sort of analogs of factorization, and boundary structure is even richer and more interesting. Similarly, in the surface story, we can think about the heart are these U variables and these binary equations and so on, the U equations. But that also generalizes well away from surfaces. There's this, as Hugh was describing, there's a sort of large zoo of objects that descend in some way from gentle algebras and quotients of gentle algebras and so on. Only some of them have to do with surfaces and a direct physical interpretation, but all of them have U equations. All of them enjoy this property of some kind of factorization that when a U goes to 0, all the incompatible ones go to 1. And the amplitudes, quote unquote, that we would define in this way have the same qualitative kind of factorization properties. So I think a fascinating general question is there anything special about those instantiations of these fascinating mathematical objects that connect to physics? So, so here I think I have time just for one question. Let me phrase this in this surface world. Oh, can I share my screen? I'm not sure.
Yes, you should be able to. You are a co-host, so.
Yeah. Oops, what happened? Sorry, guys. I should have done this earlier. Oops. Okay. Do you see my screen now? No. Sorry.
Not yet.
Many apologies. Share my screen. Okay. There we go. All right, so let me phrase this. Let me phrase at least one avatar of this question in this world of U variables and U equations. So if you were to ask, your garden variety string theorist, what's special about the string worldsheet and the two-dimensionality and strings and so on, probably the second or third words that would come out of their mouth is modular invariance, modular invariance, modular invariance. And that's because when you work with string amplitudes at loop level, you start seeing these magical functions like the Dedekind eta function and Jacobi theta functions showing up, and their properties under modular transformations play a sort of crucial role in the physical consistency and a correct interpretation of the theory. So we can ask, where do these objects come from in this new way of thinking about things using U variables? And one of the things that sort of bothers you when you first think about these surfaces is the proliferation of these infinities. There's infinitely many curves. They can self-intersect infinitely often, wind infinitely often. Certainly, at least if you're me, you first run into them, you're like, oh, this infinity is bad. You want to get rid of this infinity or truncate it or somehow deal with it and somehow mod out by it. But in fact, the infinities are really good. The presence of these infinitely many curves is what is made crucial use of in the formulation of string amplitudes at loop level in this language. And so let me give you the simplest version of this, which is already in the case of the once punctured disk, where the curves that we're talking about are either this, they're either, there's just two kinds of curve. There's this one spiraling curve, so we can call that guy Y, and then there's a curve that goes around the puncture and intersects some number of times, let's say, Q times, okay? And all of these guys have U variables, and I'll just tell you, this is a one-dimensional problem, so there's one variable Y. The U variable for this capital Y curve is just this variable little y, and the U variable for the self-intersecting curves that intersect Q times look like, as Hugh was explaining, a ratio of F polynomials of this form, where in this case, FQ is just 1 plus Y plus ... plus Y to the Q. Okay, so that's, and of course, since this is a geometric series, I can also rewrite this as G of Q minus 1, G of Q plus 1, O of G of Q squared, where G of Q is just 1 minus Y to the Q plus 1. All right, so, okay, so you can readily verify that these U's satisfy the U equations and so on and so forth. But now there's an interesting question. If you're going to have these infinitely many curves and none of them have any standard momentum, so if we're going to put them in the U equations, you want to sort of decide what exponents, what product of UQ, some numbers NQ. You want to figure out what these numbers should look like, what these numbers should naturally look like. And the fact that we have this q minus 1, q plus 1 over q squared property tells us that this is nothing other than 1 minus y times the sort of product of 1 minus y to the q to the discrete double derivative of these exponents. So nq plus 1 minus 2nq plus nq minus 1. So this makes it clear that if these n's are either a constant or the scale linearly or scale quadratically, this discrete double derivative is just at most a constant or 0. So that's going to be one kind of answer for this product, or it could scale. The exponents could scale faster, and I'll get products of these guys raised to higher and higher powers. So for example, if nq are all equal to 1, this product is 1 over 1 plus y. If the nq is equal to q, the product is 1 minus y. That's what shows up in the u equations. That tells me this plus a u for y is equal to 1. And if nq equals q squared, what I get is 1 minus y times 1 minus y squared, 1 minus y cubed, blah, 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 all to the power, all squared. For higher nq, if it's nq is q cubed, then I get something here where the powers increase with the q. But I want to highlight this case. Okay, so because in this case, what I get, remarkably, is a Dedekind eta function. Okay, so up to a factor of 1 minus u, this is 1 over 1 minus y times, the Euler function squared, where 5y is just the product of 1 minus y to the k over k. All right, so that's fine. If we take these infinitely many curves and we raise them to these interesting quadratically growing powers, then we get this famous function that has modular properties. So this famous function has the property that a to the quarter, e to the minus a 12th, a 5 e to the minus a equals the same with b, e to the minus a 12th b, 5 e to the minus b when ab is equal to pi squared. Okay? So my question is, where the hell does this come from if you don't know anything about Poisson resummation, if you don't know anything about the usual ways we think about these things? From the perspective of quiver representation theory, cluster algebras, all the stuff that we know and love that goes into this story, now that we have infinitely many curves, these interesting kind of products show up, and some of them have magical properties that seem to take us totally outside the world of ideas that went into their construction. So a concrete question is there an analog of this phenomenon for the other cousins of the surface world, the cases where we have u variables, infinitely many of them, where they're under control, we understand them, they come from gentle algebras and their quotients. But is there an abstract meaning to these exponents going like q squared? Is there an abstract analog of this object that generalizes these famous, amazing things like Dedekind eta functions and Jacobi theta functions to more general settings? Or is their presence really, really special about surfaces? In which case, that might give us a clue that there is something very special about surfaces in this story after all. Thank you.
Okay, thank you, Nima. I think, is there anyone who wants to address the possible answer? I don't know if you, Tom, you have any comment or? Okay.
So maybe one possible question for you. These questions have been cut through the algebras. So there are some more general settings where similar things appear. So.
Nima, can you hear what Alex said?
No, can you say it again? Sorry, I didn't hear you.
Can you shout?
A keyword like cuts through the algebras. So in this theory, these kind of equations appear naturally. So
In Katsumodi algebra, these kind of equations appear naturally. This may be the summary. Or is it a question or maybe an observation?
it's kind of not a question.
It's an observation, I think.
Well, yeah, anyway, but there's really a concrete question, because we really have lots of cousins of these surface things with the same qualitative properties, totally under control. We know what the u's are. We know what the equations are. But the question is, for one of these quivers abstractly coming from a gentle algebra, do we know how to define these kind of objects that satisfy these, that have these remarkable kind of properties? And if so, where do these properties come from? Do they have a combinatorial meaning, origin, somehow? Or do we have to completely exit the combinatorial world and enter all the standard ways of thinking about these things from Poisson resummation and this and that I think it's an extremely interesting question.
Okay. Oh, yeah, you has to say something.
I guess I'm not sure I'm not sure how much more there is to say in the gentle world, just because I feel like, one curve is kind of as good as another. They're all going to have the same kind of behavior. But I do think that it's interesting, what happens if you look at like the algebras that one would use to categorify like a Grassmannian cluster algebra, for example, which is, so that's far from being a gentle algebra. But yeah, I mean, I alluded to this kind of point in my talk as well.
Yeah, but even in these cases, which are I think closer to, I agree with your first comment, but even there, the question is really, what's the meaning sort of abstractly of these exponents going like q squared? What's the meaning more abstractly of these good modular properties and so on, other than this sort of specific example? Does this phenomenon sort of lift to something that is meaningful in these more general settings or not?
Yeah, absolutely. But I think we need to leave the gentle world to find that, because I think that in the gentle world there just isn't. I think we kind of have exhausted what's going on in the gentle world, and that's why we need to push further.
Okay. Thank you. Nima, you heard the last comment?
Yes.
Okay, cool. Okay, thank you very much. You can stay online for, if you want to make any comments, just write a message and we will unmute you. We can proceed with the next open question. And Mark, you want to give the next open question? Yes. Right here.
Yeah, well, thanks for leaving it to me to ask the biggest open question in amplitudology. I'm going to start by phrasing it in a more provocative way, which is prove the least or best upper bound on the computational complexity. Let me say on the asymptotic complexity of computing tree level n point nk MHV amplitude. And there are at least two interesting notions of asymptotic that you might consider. You might consider n to infinity with fixed k. Or you could consider like a diagonal limit that probes the most complex amplitudes, which would be n and k to infinity with k like n over 2. Okay. And maybe a way to put this kind of abstract question, which is outside the realm of terminology that most of us are used to, maybe the smoking gun that we're all looking for in answering this question is what is the dual amplituhedron? So let me just say a couple of brief words. I have some notes here, just like one formula. Didn't have time to put it on paper. I just wanted to make sure I get all these factors right. Okay, so the whole point behind the amplituhedron is that we have this space and we're tiling it. So for example, the n equals 6, k equals 1 amplituhedron, when you tile it using BCFW, it has 3 pieces. And the canonical form on this positive geometry computes the tree level amplitude. So there are different ways of tiling it into 3 pieces, and those give you different expressions for the amplitude. So one expression might look something like I should save time by using twistor coordinates. And I skipped one. Why? I want to get some formulas here. for which one would I take? 4, 5, 1, 2, plus 2 similar terms. Okay. Where each term, so the overall form would be the usual top form on this space times this quantity. Okay, so the only reason I'm writing this is to emphasize what many of you know, that the individual pieces here have spurious poles, which have to cancel in the sum. So for example, in this one that I've written here, this is a spurious pole, and 5, 1, 2, 3. These two are spurious poles. So when you add these other terms, they cancel the poles along those lines. Okay, so the reason I'm writing this is there's a version of the problem where you can take the tree level amplitude and you can multiply it by a factor which looks like this: I plus 1, j plus 1. This factor accounts for all possible poles that can exist in any amplitude. And let's call this like the amplitude numerator. Okay, I'm going to call that the amplitude numerator. So this thing is guaranteed to be some giant polynomial in Plücker coordinates that can be represented in many different ways. And so the problem of finding the dual amplituhedron, Thomas alluded to this in his talk when he talked about the canonical form of a polytope and it being expressible as the polar of the dual of the polytope. So what is the theory or what is the mathematical construction that can just hand you this polynomial on the nose? Okay, and that can be expressed, and I like thinking of it as a computational complexity problem because this amounts to, so because this thing is a giant polynomial in Plücker's, the problem of computing a tree level amplitude, there's a certain map from, if I get this right, we're talking about a map. Let's choose all of our, let's choose our kinematic data to all be integers, right? Then we're evaluating some giant polynomial. So we're going to get an integer out. Okay. The tree level amplitude after we pull out this factor is going to be another integer. So we're talking about proving the best upper bound on the computational complexity of a certain very well-defined map from this space to the integers. It's really just a computational complexity problem. So I'm intrigued by the fact that every tiling of the amplituhedron, as far as we know, has the same number of tiles. For m equals 4, it's given by the Narayana number. It would be extremely interesting if there's another way to compute this form that has asymptotically fewer number of terms. I've bothered you guys about this kind of before. And it might just require using things that are bigger pieces than what you call tiles, or it might require something that was referred to in the questions at the end of Melissa's talk, where here's the amplituhedron, and maybe instead of breaking it up into tiles like we're doing now, you want to break it up into bigger pieces, but allowing yourself minus signs so that you can cancel, right? So because the experimentalist who wants to compute these things for their experimental analysis, they just want to compute it as quickly as possible. They don't care that you have this beautiful collection of terms that all come with coefficient +1. They'd be willing to throw in some minus signs in their code if it runs asymptotically quicker. So I've probably used up all my 5 minutes, but let me just quickly check my notes to see if there's anything else. Yeah, I think that's good enough.
Thank you, Mark. Any comments? I would add some comments. No?
Yeah.
But yes, yes,
So maybe kind of little question.
also
about
you
this
might
spurious, you mentioned there was some like one theory. Write down, pick a tiling.
Yeah.
Marginal tiling, so that it will be spurious. False, but for example, suppose we want to see that this is pole is not really a pole, so we can find another tiling.
That doesn't have it, yeah.
Is it actually true that like if you consider poles that for which there exists at least one tiling that don't appear, so then they're actually poles.
Yeah, if I understood your question correctly, yeah, for any given spurious pole, you can always find a different tiling that doesn't have it. Yeah, and thank you. That allowed me the opportunity to add something I forgot to mention before. After you do this rescaling, you know that you're going to get an integer, but each term here individually is going to be rational. So it's kind of the cancellation of spurious poles can be phrased as the non-trivial addition of a collection of a Narayana number, rational numbers that all add up secretly to an integer.
Yeah, brief comment. So in the case of k equals 1, for the amplitude that is a polytope, or in general, in case of polytopes, if you want to compute their canonical forms. I mean, this question has a clear answer in terms of the numerator has a clear interpretation as the adjoint of the polytope, which geometrically is called the residual hyperplane arrangements of the facets of the polytope. So your computational question, you're phrasing in terms of like signed tilings, but geometrically as the other side, which is finding the residual hyperplane arrangements, meaning the facets of the amplituhedron, if you take the Zariski closure, they will intersect, let's say, outside of the amplituhedron, and these intersections will create poles in the denominator of your canonical forms, unless they're cancelled by something in the numerator. So the numerator encodes all the intersection of the Zariski closure of your facets of your facet geometry outside of the semi-algebraic set. And in that, so for polytopes, it's proved that there is a unique hypersurface of the right degree that passes through all these bad intersections, and those are exactly the zeros that cancel the bad poles, and that's the numerator of your canonical form, so it's answering that. But the equivalence for the amplituhedron is not known. I guess this was also the question you wanted to say later, so we're discussing it now. So if you want to.
Oh, did I steal your thunder?
Should I continue or?
Yeah.
Well, you can.
You can
either continue or the discussion, or if you want to write it.
I mean, there were no more questions for Mark, then I
Well,
will.
you can also take my questions.
Can I make a comment?
Nima has a comment.
Yeah, can I make a comment? So I of course absolutely love this question. I want to make actually two comments. First, it might be worth thinking about what you mean by the large N limit, even slightly more precisely, because if you think about the sort of picture of a dual polytope, if you imagine that we go that N goes to infinity in such a way that all the sort of vertices of the polytope actually lie in a smooth curve, so that the limit is actually the convex hull of some kind of smooth surface, then you could even imagine sending N to infinity and just computing the volume of the dual by Monte Carlo, throwing dots, right? And so that's like a shockingly fast way of getting the answer. If we imagine that the N goes to infinity limit, the kinematics is not random, but is actually limiting to something smooth, which is actually physically quite relevant. So that's one point. Something else I'll say, and this is maybe a place to make some link between the world of the amplituhedron and the things that we're learning from surfaces, is as you probably heard from Carolina's talk, we understand that these amplitudes have this huge set of zeros. You can think of these zeros as also, of course, zeros of this numerator, or the cousin of this numerator, portrayed by cube theory and its cousins. And it's a remarkable experimental fact that simply knowing where these zeros are and nothing else, zero, nothing about the poles, factorization, nothing, just the pattern of zeros, experimentally is enough to completely determine these numerators. So I think it's a sort of wonderful conjecture that maybe these numerators are like the determinants of simple matrices that scale with n, so that in fact the computational complexity is ridiculously small. They look like they expand out to lots and lots of terms, but in fact they're secretly a determinant or something like that. That would, I think, be the most sort of glorious thing. And I think a place where we might try to make a connection between that world of ideas and the amplituhedron is to ask and answer the following question. In the amplituhedron, how can I degenerate the external data, keeping it positive, but maybe going to the boundaries of the external data space to make the shape of the amplituhedron simpler and simpler and simpler, perhaps finally to simplify it to the point where the entire amplituhedron is the image of a single BCFW cell. So that's a nice question. I mean, can I simplify the external? Well, obviously, for polygons, it has an obvious answer. I can degenerate the external data so that they all lie on a triangle, and then the entire amplituhedron is the image of the one cell that goes along with that triangle. The question is whether that has an analog for general M and K, and that might be the sort of beginning of finding a connection between the two worlds. Because on the side of the surfaces, the beginning of understanding where all these zeros and everything comes from is simply the realization that the objects are Minkowski sums of simple pieces. And so said backwards, you can degenerate the external kinematics so that the object becomes as simple as possible. So it might be worth understanding what that locus in kinematics is where the amplituhedron itself degenerates to something as simple as possible. And I think that's also related to the long quest of trying to discover what the dual of the amplituhedron is.
Thank you.
Thank you.
I think for M equals 2, we know what this thing is.
Yes, for M equals 2, we know. Yes, I meant for higher M.
Okay, Thomas, come up. I stole your
Yeah.
thunder.
Oh, no,
Yeah,
no.
let's try to be brief because we already discussed about dual amplituhedron. Unfortunately,
Yeah, so,
We're not
my problem was what's the dual amplituhedron, which I mentioned in my talk. So so just to mention something that I don't think has been mentioned, but the one of the evidences for the existence of a dual amplituhedron is the fact that empirically the amplitude, the canonical form of the amplituhedron is positive inside the amplituhedron. So you have your positive geometry, and you ask whether this thing takes the same sign, so constant sign in the interior. And this, I believe, has been checked with amplituhedron, appears to be true. And this is some kind of evidence because in the case of the polytope, there's this formula that I wrote down in my talk. When X is in the interior of the polytope, you define the polar polytope, and the volume of that is a positive real number. So that's some evidence. So I have a vague suggestion for how to try to. I mean, this problem has been around for a long time, 10 years, to try to find the dual amplituhedron, but we haven't gotten anywhere. So here's some idea for trying to do it. One thing. So if I take my example of the quadrilateral and we looked at analogs of triangulations, and there's a formula for the canonical form when you triangulate the quadrilateral. There's also a formula for the canonical form when we do what we've been discussing, which is to do a sign triangulation, and one of them is to take this, you write it as this big triangle minus this small one. So minus this one. And this corresponds to, so if you check this actually corresponds to a triangulation of the dual. So if you manage to find a sign triangulation of the amplituhedron, you would be exploring some feature of the dual amplituhedron. And so now that we understand many things about triangulations, I'm curious what we understand about these. One feature of this triangulation is that it doesn't use any hyperplanes that weren't already in the original problem. So I'm only using the 4 original hyperplanes, and I want to triangulate, but I'm allowing signs using the original hyperplanes. So that's the so there's multiple versions of this. So there's a version that's geometric. There's a question about amplitudes. Do you have a formula for the amplitude that Mark wrote down? A formula such that everything is sum of terms that have no numerators, but all the denominators are amongst the denominators that you expect in the final answer. In terms of commutative algebra, I'm asking you to take a rational function on the Grassmannian and do partial fractions on it. I want to take a rational function on the Grassmannian, write it as a sum of terms, which is like 1 over products of the things which are facets, 1 over the product of facets, and I add a bunch of terms together. And the question is, do we know how to do this? And what are the possible ways of doing this for the canonical form of the Amplituhedron.
Okay, thank you. Yeah.
Yeah, so I think no questions, right?
No, it's okay. We can discuss. Yeah. I mean, I think one brief comment is that, yeah, of course, in order to do that, one might have to leave the Amplituhedron and go outside. So instead of the positive Grassmannian, one would have to go beyond the positive Grassmannian in the domain and maybe applying similar maps. And maybe it relates to some non-planar diagrams, functional diagrams, or a planar Clavic graph, which seems an oxymoron. To do that, that would be very interesting to do.
Can I make a concrete suggestion about this question, Thomas? So I think something which is even stronger than the positivity is that there's a monotonicity. So that if you imagine you have some z's, and then let's say you add one more z, keeping all the other ones fixed, but you just add another z, keeping everything positive and keeping y the same, then you're sort of making the polytope language, you're making the polytope bigger, but you make the volume smaller.
So you check that increases the value?
Yes, that's right. And I think there's a natural conjecture, which I have not checked actually, which is that if you imagine positively parametrizing the z's with some positive coordinates for the z's, that as you increase the positive coordinates for the z's to make them sort of more positive, or if you like, you head towards a boundary and then you locally go away from the boundary, that the sign of the amplitude is always that the derivative that it's monotonic. So I think that's kind of a differential version of this question, and maybe that differential version will be useful for figuring out what small chunks of the dual look like, rather than trying to find whole big triangles, which is what we've been trying for a while.
Yeah.
It's a strategy. I just haven't worked on it, but I think that might be a way to go.
Okay. Thank you.
Yeah.
Thanks, Nina. Any comments? Yeah. There's a question there.
Is it obvious how to write any polytope as signs of synthesis involved in the hyperplanes?
I don't know if it's obvious, but it is a known thing that there's a version in the polytope algebra. There's a duality map in the polytope algebra. There's something called filament duality, something called Kuperberg duality, which are different versions of.
Can you take a triangulation of the dual polytope?
Yeah, so if you have a triangulation of your polytope, you have a formula for the canonical form. If you have a triangulation of dual polytope, you also have a formula for your canonical form. And this is related to, this is a shadow of things that we know in the polytope algebra.
Thank you. Any more questions? Okay, so now we are going to, thank you. Going to go to some other questions, and I'm going to list the keywords that the person suggested the open question. So please, the person who connects to these keywords can come and suggest a question. So I can read here: total positivity, cellular decompositions, and conjugacy classes. Is the person who suggested this question? Okay, please, okay, come here. You can also introduce yourself. I can help you erase it. Sure.
Do I speak louder?
Yeah, as loud as you can.
Okay. So there is one big puzzle to me in the study of total positivity that when you get a positive structure, you always decompose it into cells, like for the cellular decomposition. And I really don't know how do you get this stratification so that the intersection of the positive geometry is a cell. But so I guess there is some vague conjecture from the cluster algebra and the Poisson geometry that this gives such a construction. Anyway, I want to start with the G positive, which is the total and negative part of the G of the reductive group, where G is a group. And to define this guy, you need something called unity. So it is maximal torus, 2 borrowing subgroup. So these are the simple loop 1 parameter subgroup. and V plus intersect V minus this T, which means that they're opposite to each other. So it is a theorem. I think the theorem due to logic that if you look at the intersection of the totally non-negative part with the two so-called double block cell. So this is isomorphic to R positive to the length of G plus the length of W1 plus the length of W2. And for me and Zelinsky actually get like a description or characterization of some element of when an element inside this double block cell is totally non-negative. And this, I guess, had a lot of connection to the cluster algebra. So now I want to look at C plus in G is a conjugacy class. And I want to ask the question. I want to look at the topology of this intersection. So this look very bad at the maybe it seems like a random question that you will never be interested in. And what's more is that because G positive non-negative is just a monoid, so you cannot take inverse of the element. It will go upside of G non-negative. And but to consider this guy, you need to take the conjugacy action, which needs to take inverse of element. But one thing so it is a joint theorem. We shown that when C is unipotent, which means that it is a unipotent conjugacy class, then this guy is isomorphic to R positive length of W. Oh, sorry. Is either isomorphic to R positive length of W1 plus the length of W2 or MT. And for every pair W1, W2, we can determine C explicitly, and also we have this. I think C has some nice property in terms of the in terms of like classification of unipotent conjugacy class. Yeah, so this and also I think if you compute some examples of this one, then it looks like it is quite good. I think that's my question.
Okay, thank you. So it's about the topology of the conjugates classes. Okay. Maybe anyone who knows about autopositivity and conjugacy classes who wants to say something or ask some more questions? Yeah.
So just because so if you model these double graph cells, right? Model by torus action.
Yes.
So that basically should be isomorphic to this thing, or
yes.
how is it related to?
Yes, I think so. Yes. Yes, you just model up the powers. So basically, because inside this guy, you just get like T positive. So and you cancel out the rank that I mentioned.
So I guess like in case of for people who are familiar with the graphs,
Okay.
that would correspond to taking the Detroit cell and rescaling it by torus action.
Yeah.
So for H variables, but the boundary H's we kind of allow arbitrary parameter or scale by parameter, model parameters. Is it related to?
So I don't quite get the.
Well, I'm trying to make a kind of
Connection.
analogous
Yeah.
notion for your question in the world of Algebras. So that's probably should be related to.
Yeah, I mean, if you rescale the columns, then yeah, the phase variables of external faces
Yeah.
of the boundary faces are get
By
rescaled, yeah,
external faces,
by
yeah.
become one or rescaled, yeah.
External with,
Yeah. But in that case,
But in that case, that is not related to conjugate. That's
okay. Well, I don't know.
Yeah.
I don't know. Okay. Other questions or comments? Okay, so thank you for your question. Okay, so we have maybe we can, yeah, we have time for maybe one or two other questions. So the other question is about surface formula and KLT. Person, yeah. Are you okay? Hi. Yes. You can write there.
Okay, so if this is imprecise, Matteo is to blame because he said, don't be shy. My understanding of this surface picture and how to get the Yang-Mills amplitude out of the surface picture is that you have some integral that looks like a D-log form, and then you have a product over these U variables that Hugh gives us a lot of information about. And you take a product over all possible curves. I think Yang-Mills might be a square. And then these curves are, you look at a disk and you mark endpoints on this disk, and you talk about curves on this disk. Now, for anyone who has seen a string integral, this is very evocative of a string integral, but string integrals have the property, well, they have two important properties. One, that they behave well when you move points around. So if I move this point across this point, the integral satisfies something called a monodromy relation. And the second thing is that when I look at, so let's call this A, when I look at products, when I look at sums of products of these A's with differently ordered marked points, then I know that this gives me another amplitude. And this amplitude is a gravity amplitude. And I guess my question is, can you write M as now a similar form, question mark, where now you have a product over curves, except now the curves are on a sphere with marked points instead of a disk with marked points. So basically, can you do KLT for the surface integral directly? Yeah.
Thank you. Yeah. So in that case, it's a complex integral, and in this case, it's a real. It's the real part of that.
Yeah.
Okay. So I guess with a physicist understands this from the string theory part, but I don't know if you. I mean, if Nima is here, no. Okay, no, he left. Yeah, that's a good question. Thank you. I don't know if yeah, you have some comments?
So when you use these KLT relations, you're gonna get an integral over two sets of these variables, right? Do you expect it to be reducible to one?
That is exactly how it works in the string case. Yes. So in the string case, you have variables that tell you where the marked points are on the disk, and then you can map them very specifically onto points on the sphere. Yeah. So I guess my question is, can you then map the curves on this disk, the curves on this sphere, and write then a gravity formula in such a way? Of course, what this form will look like is probably very different from the D-log looking form over here, but yeah.
Allowing by in complex, right?
Presumably that's what you have to do, yeah.
On the M, should there be like dy bar, and like usually it's u squared essentially.
I have no idea what this should look like. That's kind of my question.
In a sense, you're saying if you put this like this thing both inside here, and then you should have a kernel and integrate everything. I think she wrote it
Something
after.
like this.
Maybe you wrote it after the integration, after everything.
Yeah, you'd want this to look then like a closed string.
Yeah.
Yeah.
Your question? Yeah. Would you comment?
I don't know if this isn't necessarily an answer, but in this stringy formulation,
there is a way, just like to get, colored vectors and get gluon, there's a way to do it for every spin. But in higher spin theories, it's just sort of sick, right? Because there's no such thing as a color theory of spin two particles. I'm not sure how that relates to this debate. I know there's a way to get it out of the string.
So in the open string, the higher spin stuff has mass. Yes. So it's quite different,
yeah.
I think.
Any, I guess?
I mean, certainly you could take our polygon and just take 2 copies of it and glue it together and get a sphere with this number of, with the same number of punctures, right?
Mhm.
And in that way, there is some correspondence of some subset of curves, or the curves on our polygon and some subset of curves on the sphere.
Right, so that's exactly how string theory works pretty much, but that involves being able to move points across one another on the disk and understanding what happens to this integral when you do that. That's how you glue it together with different configurations. That's basically what this does.
So on the sphere, that would correspond to like twisting the two adjacent, twisting to
The disks with one another, I think, yeah. Yeah.
That's a great question. I don't know if you has a insight. Maybe it's too early. But I should think about gluing two integrals and if you get something up.
Okay.
Not sure. Okay, thank you very much. That's a great question. Okay, maybe we have the time for one last question. It's about negative geometry, symbols, and cluster adjacency.
Oh yeah, it's my question. But I think it's very specific, so I realize that maybe it's better if I ask it, right?
Oh, okay, up to you. Okay. Then we can move to the last question. So it's about non-realizable. Okay, it's actually a long description. Algorithmic construction of canonical forms for rank 3 oriented methods and the scattering equations. Open questions. The discussion was give 3 keywords. The keywords are.
Try, I wrote 3 keywords.
I should have said maximum 3 keywords. Okay, non-realizability, spurious boundaries, and free parameters. That's the 3 keywords. Okay, thank you. Yeah. We have a maximum, 5 minutes.
That's fine.
Yeah.
No, the context, there's a little bit of context, which is, if you want to write down the canonical form of the Amplituhedron, you can do some BCFW tiling, or you could do something a lot finer into realization spaces of oriented matrix. So the question is, if you have a sign pattern of Pluker coordinates, which is realizable, which I'll represent as some configuration of lines. Okay, I'm going to get the canonical form of the region in the Grassmannian described by this configuration of lines. Okay, so how to do that? Well, I'm going to take each triangle here, and when each triangle shrinks to a point, that sends me to a boundary of that particular point, that particular cell in moduli space. Okay, so we have 1, 2, 3, 4, 5 boundaries. Okay, so we label these guys like 1, 2, 3, whatever. And so we get, in this case, we get 2, 3, 4, 3, 4, 5. And we get this point represents, this diagram represents a point in the interior of the positive Grassmannian. Because it's a nice convex pentagon. The question is, when you start having more and more lines, you got up to like 9 and 10 lines at once, well, you can start running into things that are called non-realizable oriented matrices. Okay, so those arise when you have you take a circle, take n points on the boundary, 1, 2, 3, 4, 1 prime, 2 prime, 3 prime. And instead of drawing like an arrangement of lines in the interior, you suddenly allow curves. Like so. So you can do a similar game. You can say, I'm going to try to draw a canonical function associated to this pseudo curve arrangement, the pseudo line arrangement by selecting all the triangles. Question is, what happens when you try to play this game when this is non-realizable? When you cannot straighten these lines without crushing some of the triangles. So this came from some joint work with Freddy Cacciazzo and Yang Zhang. And what we found was that you can make an ansatz by taking the product of all the denominator factors, delta 1, I, maybe n. And when you try to figure out what the numerator has to be, such that it turns into such that you get the canonical form for a positive geometry, well, that numerator might also contain delta I1. Where delta I1 is the guy that has to be killed when you have to straighten the line arrangement. So the question is, what happens to canonical forms for realization spaces which are not realizable? You can always make an ansatz for what it will be, but what actually happens to the form for a non-realizable or oriented uniform matrix?
Okay, thank you for the question. Okay, any questions or comments about this? I think I would have a question. Could you explain a bit better how do you find a canonical form for non-realizable? So you start from an oriented matrix.
Yes.
What's the recipe to cook up the canonical form?
Right.
I mean, I know for realizable, I mean, you just
realize
the region, and that's conjecturally or maybe in practice.
I mean,
I understand that you basically, if you think it linearly, you cannot realize it in a configuration of lines, so you cannot twist the line in a canonical way or make some curves in a canonical way such that it corresponds to non-realizable. But is there a canonical way to draw that picture that you drew from an non-realizable matrix?
So there is an algorithm to do it, which is it's an exhaustive algorithm, exhausting and exhaustive algorithm, which is you list all of the oriented uniform matroids for a given n and rank.
Yeah.
For each of those, you make an ansatz for the denominator and for the numerator. When two tiles are adjacent, when two oriented uniforms are like flip adjacent, then you ask that the two canonical forms coincide up to sign on that boundary. So to answer your question, what it can be is that you can end up with an actual realizable line arrangement, which is adjacent, which is flip adjacent to a non-realizable guy. So you can start to put constraints on.
So there is a notion of adjacency between oriented matrix, including non-orientable ones. And for each one, you can make an ansatz, and then the adjacency puts a constraints on that, and then somehow you fix it.
That's our exhausting algorithm.
Okay, it would be interesting. Yeah, it has the canonical meaning.
So the idea was, I mean, given the canonical function of the Amplituhedron, like how does it reside with respect to these non-realizable pseudo-line arrangements, pseudo-sphere arrangements?
Yeah, interesting question. Any comments from the matrix work? Yes.
Formula for canonical form?
Is that there is an exhausting algorithm?
Okay, suppose you start moving one of these lines until one of the triangles flips.
Yes.
So I guess canonical form for first arrangement should be related to canonical form for the other arrangement by simple transforming.
Yeah, no, the residues on that configuration.
The residues actually coincide.
Yeah. It's a cancellation of a spurious pole if you think that things is tiling some bigger space of.
Yeah, basically, the question is how to do it for non-realizable.
How to do it for, so there's an ansatz, you can always make an ansatz for a non-realizable oriented uniform matroid. You get the denominator from the set of triangles, from the set of simplices. You can make an ansatz for the numerator. You can start to determine some of the coefficients in the numerator. And the question is, what happens at the end of the result to that canonical form? Like, can you fully determine it? Does it see all of the fake simplices in the pseudo line arrangement, or do they disappear? Do some of them disappear, like what we found with an n equals 9 case?
So if you add up the canonical forms of every possible uniform oriented matroid, you should get 0.
If you choose the sign right, yes.
If you choose sign right. So would you get 0 if you omitted the non-realizable ones, or would you?
Yeah, so the best way to answer that is, yeah. We implemented our algorithm and found some free parameters. There are some free parameters remaining, and I think we discussed this. And so even if you insist that that summing over everything, you have to get 0, including the non-realizable guys, then those free parameters remain. So my feeling is that yes, you have to include them, but somehow they'll be, it's kind of fuzzed over somehow.
I think it's interesting that they sum up to 0 because we got also in a recent paper for M=2. In that case, the oriented matrix are very easy, or permutation equivalent to the positoids GR2 command. But if you specialize the ones for which, I mean, the regions, I mean, we basically consider certain regions where some Bruckers have certain positivity given by the Amplituhedron. We get that if you define this region for each k, for m equals to Amplituhedron, and you sum this region for all k, then the canonical form of the whole thing is 0. But it's not, I mean, it's not the whole it's not the whole possible regions in the real Grassmannian GR2 command. Are the ones for which like pi plus 1 positive, for example. And if you just do that, you get 0. You don't have to sum over possible. No, it's just interesting to understand. We don't have an answer. Like, what is the meaning that the sum of canonical forms of the region is 0? I mean, I don't know how to interpret. I mean, unless you say that the boundaries are matching up with different orientations, that everything cancels. But we don't have a geometric understanding of why certain things are 0, other than being able to prove that it's true algebraically. So that would be interesting to discuss. Okay. Any questions? We should wrap up soon. Okay, so if not, let's thank all the speakers of the day and all the people who have formulated questions and as participated here. Thank you very much.